and then we let it slide, and assuming, of course, it doesn't stay in place, if it slides, what would be the works and how might we compute them? So let's go ahead and put in, I'll call this theta, I don't know, let's make it a tangible angle, 30 degrees. I'll put in all my forces. Force of gravity is always downward. Normal force is always perpendicularly away from a surface. And of course, if it slides down, then kinetic friction will act up against the motion. I'll go ahead and put in the displacement vector as well, putting it in a different color because it's not a force, but it is a useful arrow that I need to compare against all the forces. Specifically, I need to get the angle that each force makes with that displacement. So let's go as far as doing the force and then the angle between those forces, each force and the displacement. Let's start with the normal force. What angle does that make with the displacement? What's this angle right here? 90. So that one's easy. You don't need to know any of the numbers. What's the work? 0. Once again, we find that normal force plays a guiding role. Okay? So it just guides the thing along the surface. And it makes sense, right? In both cases, the normal force was perpendicular to the motion. Let's do the other ones. Friction. What's the angle between the displacement and the frictional force? What's this angle here?
180.
180. What's going to be the sign of that work? It's going to be minus. I guess I can write it like this, label them. So friction is the tax man again. It's going to take away kinetic energy. Now, if I release the object from rest, there is no kinetic energy to take away. What is the thing that's going to add the kinetic energy to the object? What is it that friction is taxing? It's the work from the pulling force, right? Or sorry, from the gravity force. That's the only one that's left. So for that, this one's a tricky one. I need this angle. What's that angle? 60 degrees. It is less than 90, which means that the work here is going to be positive. Now, one of the things that I do want to make sure to point out, the angle of the incline was 30 degrees. Where do we substitute 30 degrees in? Nowhere. 90, 180, 60. I don't carry around this big subscript for nothing. Okay? It's to really remind you that you have to identify that angle in that very particular way. So don't just see an angle in the problem and assume, oh, that's the angle I shove in wherever I need an angle. Okay? So the angle of the incline here is 30, but my three angles for the calculating the work are 90, 180, and 60. Okay? So from there, of course, you could, if you had more information, you can compute not just whether the works were positive, zero, or negative, but what their values were, and do it similarly to the last example that I just did in more detail. Are there any questions on this? Okay, so the reason why I wanted to sketch out at least two of these, right, one on a flat surface and one on an incline, was I wanted to discuss patterns. So what are the patterns that we see arising of the works done by various forces? And there are some already. So this right here, if you want to mark it down, is kind of like the cut point between homework 6 and homework 7. So homework 6 is just, at the very end, you'll find some problems that are just doing the work method, just exactly as how I've described it, where you just basically identify your forces, you find the angles between each force and displacement, calculate your works, add up the net work to get the change in kinetic energy is blah, 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 and just like I've been doing. Doesn't require a whole lot of noticing patterns of different works, you can just calculate them and do it. But here's what we're up to. So here is the kind of the trajectory. We started off with the forces method. Okay, so the forces method was homeworks numbers 4 through 6. And of course, it's probably the thing that I hope the thing you're most familiar with now. It requires being able to wrangle vectors, break things into components. And that, of course, was the basis for developing what I'll call the work method. So it's a little bit of an uphill slog to what we currently have called the work method. And you'll see this a little bit at the end of your homework number 6, just at the end. I want you to get accustomed to calculating works and understanding what those works mean. So what's next? You're probably highly skeptical at this point that this method isn't just another torture device, another thing that you have to learn. But we're just about to come down into the promised land here. Okay. And we're going to develop this into something called the energy method. And this we'll use for homework 7 and beyond. And I can pretty much guarantee you that it will become your favorite method in the class because it's in some ways simultaneously the easiest to use and the most powerful. Okay? So we're looking to develop something out of what we're doing now. And you notice that there's already certain features of the work method that you might like. Some of the features of not having to set axes or do components or anything like that. And it's only going to go more in that vein. It's only going to become easier to do and become more powerful. Okay? We already said that we don't actually need the acceleration to be constant. Now, it is in this problem, so that's why you could do it either way. But there will be problems later that you could not do with the old way, but you can do with the new way. So the energy method, the way I'm going to motivate developing it is by looking for connections between the works that I've just calculated. And there's a lot of connections that I can pull. So let me find some room. I guess, let me go over here. So this is general rules of thumb for calculating a work. So let's go back. In my problem, both of my problems, I had normal force, right? And both of the times, so both here and here, what was the work done by the normal force? 0. So is this a general truth? It seems to be that the normal force will, on a regular basis, act perpendicularly to the motion, which makes it a guiding force. It makes it a force that does not ever make you go faster or slower. It simply guides you. Guides you how? Guides you so that you don't smush the surface. It's basically saying you can do whatever you want, just don't come in here, okay? So the whole point of the normal force is to prevent motion in that axis, right? If I have something sliding along a surface, whether that surface is tilted or not, normal force allows motion parallel to it. You can't move along that, right? You can't go into the surface, so normal force won't allow that. And if you try to move along the normal force like this, the normal force disappears, right? Because the normal force only exists when you're on the surface. So the normal force can't do any work. So And by definition, you can only move parallel to the surface, and the normal force acts perpendicular to it. Now, there is, I guess, one special case I should tell you about. If the surface itself is moving, like let's say it's your hand. So of course, you're lifting something, so it's displaced upward, and the force from your hand is really a normal force as well, because of course, it's a solid surface that doesn't want to be smushed. So in that case, the normal force can do work, but this is where we get into semantics. Okay? We usually call the force from a surface that doesn't move itself, we call that a normal force, whereas if it's a normal force from a moving surface, we call that a pushing force. So we normally would call this a pushing force, and then we can safely say, well, normal forces do no work. Okay? So normal force we usually save for a force exerted by a stationary surface. Okay? So that's just semantics. It's not that the normal force can't do work, but when the normal force does work, it's because the surface itself is moving, and we call that a pushing force instead of a normal force, even though they're really one and the same thing. So the normal force can't do any work. You're talking about a stationary surface, which we usually are. Let's take a look at friction. Who do we find a common thread there? We did this on a horizontal surface. We did this on an incline. Here's your frictional force. Here's your frictional force. And in both cases, we found that the angle was what? 180. Because friction, of course, always opposes you exactly. So we already knew that from our study of the force of friction, that no matter which way you're sliding, friction acts opposite. And now, the way that that manifests in the work formula is that it's always cosine of 180. So that's -1. You can put the minus sign out here if you want to. But remember that minus sign is not directional. It comes from the cosine of 180. It comes from the fact that friction acts against the motion. So it always does negative work and always removes kinetic energy. So if you wanted to save yourself all of one step in calculating the work done by friction, you could start here. Okay? You could start here, and instead of having to identify that cosine of 180 is -1. So those are commonalities you can count on. You can use them in problems. But the big one that we need to find a shortcut for, and this is going to open up the biggest room for more possibilities, is gravity. Now gravity, question? No? That we don't seem to have a common theme for it. It was 90 degrees over here, and it was 60 degrees over here, right? So gravity was the one that didn't seem to have a constant angle between the force of gravity and the displacement. Well, the reason for that is because gravity is the one force that we can depend on to always pull down no matter how you move. So if you're moving horizontally, well, gravity always acts vertically, so the work will be 0. Gravity has no opinions about your kinetic energy when you're moving horizontally. That was like our first example. If you happen to be moving somewhat or completely downward, then the angle between the force of friction and your displacement is less than 90. Gravity will help you. Gravity will do positive work. It will add kinetic energy. When you're going downward, either in part or in full, gravity helps you go down. And likewise, if you're either partially or totally going upward, well, gravity still pulls down. So now, that angle will be more than 90. And gravity will do negative work. It will hurt you. If you try to go upwards in whole or in part, gravity will hurt you. It will take away kinetic energy. But notice the common theme here is that gravity always pulls down no matter what you do, no matter how you decide to move the object. Gravity can be counted upon to pull in a particular direction. Okay? So, there is going to be a shortcut available for the work done by gravity, a huge shortcut. Not only is it a huge shortcut, which will allow us to calculate very, very complicated trajectories, but it'll lead us right into the energy method as well. Okay? So let me see if in the next few minutes I can do something with that, and then we'll break. I want a work done by gravity shortcut. Is there some magic silver bullet that I can use to very quickly calculate the work done by gravity in any circumstance? Let me go ahead and mark off two heights. I'll say that the difference in heights is delta H. And then what I want to do is I want to take a look at various trajectories between these heights and calculate the work done by gravity. The first one is the most obvious one. I'm just going to drop a ball through the air, and I'm going to let it fall, and I'm going to ask how much work is done by gravity. That'll be my trajectory A. The next one, trajectory B, will be a diagonal straight line between those same two heights. Now obviously that's not how things fly in projectile motion, so that could not happen under gravity only. There would need to be at least one other force to allow that to happen. That still doesn't negate the question, what is the work done by gravity in this case, even if there are other works that are necessary. For trajectory C, I'm going to return to something which can happen under gravity only, which is a projectile motion flight. And that, of course, has that characteristic arc shape. So I can point out here A and C can happen under gravity only, and B cannot. But nonetheless, in all three of these circumstances, I'm going to calculate what is the work done by gravity. Okay? All right. So let me go ahead and put down my displacement vector here. Put down my force of gravity. And calculate. So trajectory path A. Size of the force, size of the displacement, cosine of the angle between them. So let's do it. Size of the force, mg. Size of the displacement, how big is the displacement? Happens to be the same as delta H, right? And just to make sure I don't get an extra minus sign creeping out in there, because I am going to a lower height, let me put it in absolute values, right? The whole point of the f and the delta x is they're not supposed to have this sign. They're just sizes. And then what do I put in for the angle? What's the angle between the force and displacement? 0. So that's +1. So there is my, and I guess I'll put the plus out front just to remind. So the work done by gravity is positive. The positive, again, means that it's going to add kinetic energy. And hopefully it doesn't surprise you that gravity is going to make you go faster as it falls, right? So that alone doesn't really tell me anything. The important thing, of course, is, well, that's my baseline. What about B? What about these other, what about C? How do those compare? So let me go ahead and write that down. Let's do B. Here's the displacement. Here's the force. Now there is some angle between them. Work done by gravity. That's the size of the force. Size of the displacement, which now I can't say that's delta H because that's clearly more than delta H. And then cosine out of that angle, and whatever that angle is, it's not 0 anymore. So you might think, all right, well, we seem to be at an impasse because we don't know either one of these. We know delta x is longer than delta h, and we know theta is more than 0. But this is where I point out that even though I don't know either one of these, I know what they are multiplied with each other. And the reason is that I can look at my triangle of distances like this and realize that if this is a triangle, delta x is the hypotenuse, and delta x cosine theta is this side, which, what is delta x cos theta? How long is this? That's this distance, right? We get the same thing. We get that the work done by gravity is the same in both cases. Now, how could that be? It seems like, how could those be the same thing? Well, here's the thing to realize about trajectory B. Trajectory B shares all the most important features with A. B can be thought of as a downward part and an over part. The downward part is identical to A, and the over part, well, on the over part, which is the second part, the work done by gravity is 0 because it's a sideways part, which means that gravity doesn't do any work there. That's why they're the same, because the vertical part is the only part that matters. When you're moving vertically, you're moving with or against gravity, and gravity cares about that. But if there's any sideways part, gravity could care less. So if we go to trajectory C, we realize that any trip can be thought of as a series of horizontal and vertical steps. The horizontal parts, anytime you're moving to the side, gravity doesn't care. And the vertical parts all add up to the same amount. The work is the same for that. If I gave you this trajectory, trajectory D, and you look at that, it's not, you couldn't even touch that before. But the work is exactly the same. The work done by gravity is the same in A, B, C, D. It's because work done by gravity depends only on height change, and all of these have the same height change. The sideways part are completely cosmetic. That's a huge shortcut, okay? So the only thing I'll really add is if we want to get rid of these pesky minus signs, or these pesky absolute value signs, the actual relationship is like this. Now, if you don't believe me, let me remind you that when delta H is plus, so you're going to a higher height, gravity is working against you, so that's why we need the extra minus sign. If delta H is minus, because you're going lower, gravity helps you, so it does positive work, okay? So that way we don't have to have that absolute value sign there. So that right there, let's knock off for today. That's a good stopping point. Do the exam on Thursday and pick this up next week. Real quick, I have a the assumptions I made for the purposes of doing the proof for you guys.
Right, and but even the proof why it's like VI should be.
Well, I can't prove the force energy theorem without making that assumption, even though